So, as you have understood, our next speaker is Elena Caviglia from Stellenbosch University, and the talk is about the exactness of the two categories of triangulated categories. Please, Elena.
Yes, so I'm really happy to be speaking at Ithaca, and I'm also really happy to be part of the Ithaca community. So thank you very much. Today's talk is about a joint work in progress with Zurab Janlidze and Luca Mesiti. And the idea is to study the exactness properties in a two-dimensional sense of the two categories of triangulated categories. And this project is part of a bigger project in which we are trying to study in general what are notions of exactness in dimension 2. So first of all, let's recall what a triangulated category is, for those of you who maybe don't know them very well. So we start from an additive category T. So this is a category enriched over abelian groups and that has byproducts. And we fix on this category what we call a translation functor, that is simply an additive and a functor on the category. And we say that a sequence of morphism that is called a triangle if it is of this form. So we start from an object X, then we have three morphisms, and we end up in sigma of X. And if we have two triangles, we can also define what a morphism of triangles is, and this is simply a triple of morphisms such that this diagram is commutative. And now a triangulated category is an additive category equipped with a translation functor and a class of triangles that we call exact triangles. And this class of triangles need to satisfy certain properties that we are going to see in a moment. But the idea is that this triangulated structure is useful to replace exact sequences. So we don't have exact sequences in a triangulated category. Maybe we don't even have kernels and cokernels. But with this triangulated structure, we have a kind of replacements for kernels, cokernels, and exact sequences. So let's see how this works. So we require that exact triangles are closed under isomorphisms, and this is a very natural condition to ask. Then we require for every object in the category to have a trivial triangle on that object. So we simply take identity of X, and then we go to the zero object with the unique morphism that we have, and we require that this is an exact triangle. And also here we take the unique morphism from the initial object, of course. And these replace the trivial exact sequences that we have of the same form, for example, in an abelian category. Then we have another axiom requiring that given any morphism in the category T, we can complete this morphism to an exact triangle. So we can find an exact triangle such that that morphism is the first morphism in the sequence. And we have to think of this as saying that A as a replacement. But this is the replacement. Another axiom saying that that being an exact triangle is in some sense self-dual, but not really. We have a kind of a rotation axiom. So if we have that this UVW is an exact triangle, if and only if this other triangle that we can obtain rotating somehow is an exact triangle as well. So this is this is obtained by taking as first morphism the second morphism of the starting triangle, as second morphism the third morphism of the starting triangle, and as last morphism we take sigma applied on the first morphism of the starting triangle, and then we have to add the a minus for technical reason. But the idea is that we are rotating and we still get an exact triangle if we start from an exact triangle. And putting together these axioms, yes? Is there a question? Maybe not, okay. So, and if we put together these two axioms, TR2 and TR3, we can get that we have a replacement also for kernels. So we can find exact triangles such that the second morphism is a certain morphism that we want, that somehow replace kernels in our triangulated category. Then we have a fourth axiom that says that every time we have two exact triangles and two morphisms f and g such that this little square is commutative, we can always complete this picture to a morphism of triangles. So we can find a morphism from z to z prime such that the resulting diagram is a morphism of triangles, and this is not necessarily unique, but it exists. And the last axiom says that if we have now a situation in which have exact triangles in these three rows, the first three rows, and notice that here in the second row we take as first morphism the composite of v and u that we are considering in the other two rows, we can complete this diagram to a diagram. We can complete this diagram to a diagram in which we have another exact triangle in the last row, and everything is commutative. And this axiom maybe is a bit less intuitive, but it's part of the structure of the part of the properties of a triangulated category. And also there are many different reformulations of the notion of triangulated category, and in some of them, for example, the last axiom is replaced by a niceness condition for the morphisms whose existence is guaranteed by this TR4 axiom. So we require that these morphisms are nice morphisms of triangles in some sense. And another important thing to notice is that we are not requiring that triangles are complexes in principle, but this is implied by the definition of triangulated category. So given an exact triangle, it's always true that the composite of the first and the second morphism is 0, of the second and the third is 0, and of the third with sigma of the first is also 0. So they are complexes. Okay, and maybe now we wonder what are examples of triangulated categories. And we are only going to see a very important example just to understand the flavor of the theory. So if we have an abelian category A, we can construct the homotopy category of complexes of A. We denote it by Ka. So it's a category whose objects are complexes over A, and whose morphisms are equivalence classes of morphisms of complexes modulo the homotopy equivalence relation. We don't really care about the details, but the idea is that we quotient somehow the morphism of complexes, and we can equip K of A of a triangulated structure, where the translation functor that we get is literally a translation. So it's a shift of 1 degree of the complex. And the exact triangles that we consider are the triangles isomorphic to triangles of this form. So here x of 1 is just the translation of the complex x of 1. And M of f is what is called the mapping cone, and it's a complex whose objects are constructed with these byproducts. And then we can construct differentials in a natural way that we don't really care about right now. And we have also these induced maps, alpha f and beta f. And we give a triangulated structure to K of A by picking all triangles isomorphic to the ones of this form. And it's nice because K of A, even if A is an abelian category, K of A is not necessarily an abelian category, but we can still equip it with a triangulated structure. So it's still a triangulated category. And we can even go one step further by constructing the derived category. So this is a localization of the homotopy category of complexes along the quasi-isomorphisms. And this category also have a triangulated structure, and the triangulated structure is simply induced by the triangulated structure on K of A, and by simply transporting this structure along the localization functor, basically. So not all triangulated categories arise this way, but they are very important among triangulated categories, the homotopy categories and derived categories of abelian categories. But going back to our original purpose, we want to study what exactness properties are satisfied by the two categories of triangulated categories. So first of all, we need to understand which functors we want to consider between triangulated categories. And the notion we want is that of exact functors. So an exact functor is a functor between triangulated categories that preserves translation up to isomorphism and preserves exact triangles up to the same isomorphism. So more precisely, it's a pair f mu, where f is a functor and mu is an isomorphic natural transformation between f composed with the translation on t and the translation on u composed with f. And it is such that for every exact triangle of this form in T, the triangle constructed this way is exact in the codomain U. And so we denote by triang the two categories of triangulated categories, exact functors and natural transformations. And we notice that these two categories has a strong by-zero object. So we mean that by strong, we mean that every time we have two morphisms factoring through 0, there is a unique to cell between them. And now, one first ingredient that we want to understand in order to speak of exactness is that of two-dimensional kernels. So in a two category with a strong by-zero object, a two kernel of a morphism F from A to B is a morphism K from K to A, together with an isomorphic two cell between the composite of K and F and 0, such that if we have another morphism, say Z from Z to A, and an isomorphic two cell between the composite of Z and F and 0, we can find a morphism U from Z to K and an isomorphic two cell between Z and UK. And moreover, we have a two-dimensional universal property saying that given two morphisms from Z to K and the two cell between the composite of U and K and V and K, we have a unique two cell between U and V, such that the whiskering of these two cells with K is exactly lambda. And if we want to see this as a limit, this is a bi-isoinserter. And we can, of course, define two cokernels in a dual way. And so now the next step is to try and characterize two kernels and two cokernels in our two-category Triang. And little spoiler, we'll find out that these are well-known constructions in the theory of triangulated categories. So when we have a triangulated category, we have different notions of subcategories for this triangulated category, but a very natural one is that of triangulated subcategory. So in some sense, it is a subcategory that respects the triangulated structure of the triangulated category. So a full subcategory S is a triangulated subcategory if every time we start from an object of X and we apply the translation functor any number of times, we are still in that full subcategory. And moreover, given an exact triangle, if two, the third one must be, so any two. And we say that the triangulated subcategory is thick if every time we have two morphisms, say pi from x to y and iota from y to x, such that if we do first iota and then pi, we have the identity on y, and x is an object of the triangulated subcategory, so must be y. And this notion of thick triangulated subcategory is very
Elena, we cannot hear you.
Exact functor, the full subcategory on the objects that are sent to zero by that functor is a thick triangulated subcategory. And this thick triangulated subcategory is understood as the kernel of F, in the sense that it's literally what we would call the kernel, just thinking of the usual notion of kernel for algebraic structures, because they are objects that are sent to zero by the functor. And another very important notion in theory of triangulated categories is that of Verdier localizations. So if we have a triangulated subcategory of a triangulated category, we can consider the set of all morphisms in the triangulated category that can be completed to an exact triangle in a way such that the third object is in the subcategory. So we can always complete F to an exact triangle because this is one of the axioms of triangulated category, but F is in M of S if we can do this in a way such that the third object is in S. And M of S turns out to be a multiplicative system, so we can localize by M of S. And we called Verdier localization of T by S this localization. So we are inverting all the morphisms in M of S. And we also have a quotient functor from T to T over S, the Verdier localization. And it is well known in the theory of triangulated categories that we can give a unique structure of triangulated category to this localization, such that the quotient functor is exact. And also the kernel of the quotient functor, ker is the smallest fixed subcategory that contain S. And this fact will be useful for us in what follows. Okay, and now maybe you have already guessed that it turns out that surprisingly all two kernels in Triang exist, and they are precisely thick triangulated subcategories. And the idea to prove this is that given an exact functor, the Fick triangulated subcategory kerf, that was already known to be a Fick triangulated subcategory, actually satisfies the universal property of the two kernels. So this subcategory that was already considered and understood as a kernel in an intuitive way is actually the two-dimensional kernel of the exact functor, and this is quite nice. And vice versa, if we have a Fick triangulated subcategory, the quotient functor of the localization, the Verdier localization, is an exact functor whose two kernel is precisely S, the starting subcategory. So we have that there is a precise correspondence between Fick triangulated subcategories and two kernels. And an even nicer result is that all two kernels also exist, and they are precisely Verdier localizations. So these notions of Fick triangulated subcategories and Verdier localizations that were already very well studied turn out to be two kernels and two cokernels in our two category. So Verdier localizations actually satisfy the universal property of two kernels, and this is not so hard to prove, just you need to work a bit, but it's not too hard. And also, given an exact functor, its two cokernel is the Verdier localization with respect to the smallest Fick subcategory that is generated by the image of the functor f. So this is also a quite a natural construction to see this as a Verdier quotient. And so we have these characterizations of kernels, two kernels and two cokernels that recover existing notions in the theory of triangulated categories. But what we have also found are other characterizations that are maybe more categorical in nature and were very useful for us to prove exactness properties for these two categories. So it turns out that an exact functor in Triang is a two-kernel if and only if these two conditions hold. So it is fully faithful, and also the full subcategory spanned by the image, actually the the image, is equivalent to a Fick triangulated subcategory. And we use this characterization to prove that two kernels in Triang are closed under composition, something that was harder to prove without this characterization, and that is also needed for our theory of exactness of this category. And we also have a dual result for two cokernels. This is a bit more technical, but it's also very interesting. So we have that an exact functor is a two cokernel if and only if it is essentially surjective on objects. And moreover, we have this condition C2 that says that given two objects in T and the morphism between the images of these two objects, we can find a span of this form such that the left leg W is sent by the functor f into an isomorphism, and such that if we compose the inverse of this image, that is an isomorphism, with f of h, we get G back, the starting morphism back. And moreover, these fractions are unique in the sense that any two such are equivalent. And as we did for two kernels, we use this result to prove that two cokernels are closed under composition, which is also very useful for us. Okay, now we completely understand what two kernels are and what two cokernels are in these two categories, and we wonder what is the degree of compatibility between these two kernels and two cokernels. Because there are many different notions of exactness in dimension 1, and we can also have different notions of exactness in dimension 2. So let's see what are some of them. So if we have a two category with a strong by zero object that has all two kernels and all two cokernels and that are both closed under composition, so the situation we have in Triang, we say that these two categories two pup exact if every morphism in the two category can be factorized up to isomorphism as a two cokernel followed by a two kernel. And this we studied this notion of two puppe exactness, and more in general the corresponding notion of two grandis exactness, so also in the non-pointed case in a previous paper. And it turns out that this notion has a vibrational characterization. So we believe that this is quite a nice notion in dimension 2, and that it's probably the correct notion of two puppe exactness in dimension 2. And in the general case, it's a bit more complicated because some of the requirements are trivial when we have a strong by zero object, so it simplifies this a lot. And for this special case, we get this nice and natural notion. But there are also weaker notions than these. So for example, we have in dimension 1 a notion of die-exact category due to Tim van der Linden. And it is a category in which every morphism that factorizes as a two kernel followed by a two cokernel also factorizes as a two cokernel followed by a two kernel. And so we can have a generalization of this in dimension 2 that we call the two die-exact. So we don't have the cokernel-kernel factorization for all morphisms, but we only have it for the ones that are kernels that already factorize as kernel followed by cokernels. So in the puppe exact case, we have that kernels and cokernels form a factorization system, while now we have a weaker condition. But we can have a notion of exactness that is even weaker than this, and this is a two-dimensional generalization of the notion of homological category in the way Marco Grandis phrases it. So we say that the category L is two homological if every time we have a morphism that not only factorizes as a two kernel followed by kernel, but does so in a nice way. What we mean by this is that if we factorize this as two kernel M followed by a two cokernel Q, in a way such that the kernel of the two cokernels, so kernel of Q, factors through the starting two kernels, so M, up to ISO. This morphism also factorizes as a two cokernel followed by a two kernel. So this is even weaker than the die-exact condition. And it's precisely a generalization of homological categories. So we have different degrees of compatibility between two kernels and two cokernels that correspond to different degrees of exactness of our two category. And so it seems like the thing to look for is which morphism can be factorized as two cokernel followed by two kernels. Is that all morphisms? Is that only some of them? Do we need this extra condition for that is typical of homological categories? So we want to study to try and answer this question. So we first characterize what are the morphisms that factorize as 2 cokernel followed by 2 kernel in our 2 category. And it turns out that they are precisely the exact functor that satisfy these 2 conditions. And these 2 conditions are not new conditions. They are precisely the conditions we saw for kernels and cokernels. So a 2 kernel was a fully faithful functor that satisfies condition C1, and the 2 cokernel was precisely an essentially surjective functor that satisfies C2. And if now we drop fully faithfulness and essentially surjectivity, and we require C1 and C2, we get precisely the exact functors that are 2 cokernels followed by 2 kernels. And now that we have this characterization, we can use it to prove that the 2 category Triang is 2 homological. So if we assume that an exact functor factorizes as 2 kernel followed by 2 cokernel with the additional property that we saw of factorization, we are able to actually prove condition C1 and C2, so we are able to prove that it is also a 2 cokernel followed by a kernel. And now the question is, can we do better than this? Is it maybe 2 die-exact or even 2 Puppe exact? And looking at the proof, we see that that proof cannot be improved, because it seems that it really requires this extra condition. And moreover, we believe that we have a counterexample showing that it is not even 2 die-exact. But we are still checking the details of this counterexample, so I'm warning you about this, but it should work. And so we have the weakest possible notion of 2-dimensional exactness, but it's still very nice. And in dimension 1, with homological categories, we can still do a lot of homological algebra. So it's highly possible that with these 2 homological categories, we can still do a lot of 2-dimensional homological algebra. And what is one last thing that I wanted to say is that we studied similar exactness properties also for the 2 category of abelian categories. And it turns out that there are many similarities between these 2 situations in a very surprising way for us. So this work about the 2 category of abelian categories is also joint work with Zurab Janelidze, Luca Mesiti, and Ulo Reima. And it turns out that for the 2 category of abelian categories, the 2 kernels are precisely what is called Serre subcategories. That is a notion heavily used in algebraic geometry. And the 2 cokernels are what is called Serre quotients, also a notion very, very, very much known and used in algebraic geometry. And we proved that if we consider abelian categories with functors between them that are what we call Serre functors, so they are functors, exact functors, that factorize as Serre as 2 cokernels followed by 2 kernels, so as Serre quotients and Serre subcategories. If we restrict to these functors, we can show that these 2 category is 2 Puppe exact. But the techniques we use and the theorems we prove, and also these characterizations of 2 kernels and 2 cokernels, are surprisingly similar between these 2 situations. So now we are wondering what is behind this. Can we understand this more deeply? And what else can be done? What other 2 categories can we consider? And there's a lot more work to do, and we are very excited about this project, and happy to hear all your comments, questions, and remarks. And thank you very much for listening.
Thank you very much, Elena, for your talk. Questions or comments?
I have a question.
Please.
Well, I don't know if I can make it precise, and I'll try to compact it because I might give an entire motivation for why I have this question. But an interesting aspect of triangulated categories and all homological algebra is derived functors. So there is this there is this probably a flaw, not a feature of the category of triangulated categories that if you didn't look into, you should probably look into because it is a form of lack of exactness. Meaning you can have in the two category of triangulated categories, if I remember correctly, absolute Kan extensions that can be computed in the two category of triangulated categories that are not Kan extensions in cut. Meaning that the forgetful functor that goes from triangulated categories to categories doesn't see colimits, and in particular doesn't see the Kan extensions that compute derived functors as honest to God Kan extensions in cut. They are a different animal that you have to treat in a different way, much like you can have I don't know, colimits in a category of algebras that are not projected to colimits in set. So there must be a reason for this. And I wonder if you plan to look into it, if you have an idea for how this can fit in the picture.
Okay, so this is very interesting. I personally didn't know about this. I don't know about maybe Zurab and Luca if they knew about this property. But yeah, I think Eva wants to say something.
I have a small comment, which is this is true also in AB, right? Because in abelian categories, coproducts and products can coincide, which means that some right adjoint, which is a Kan extension, blah blah, is actually a left adjoint, but this is not.
Sure, yeah.
Sorry, this is actually true also in cut. So yes, so this Kan extension is preserved in cut, actually, in that case. Okay, I retreat. Sorry, it was stupid. I apologize.
But I think this is very interesting and we'll look into it. I don't think we have an answer yet.
I don't. No, I wasn't implying that you have to have an answer.
No.
It might be recognizing that you can compute derived functors not only with resolutions but with Kan extensions was a little win for the two-dimensional algebra approach to homological algebra, to stable homotopy, if you want. So it is an important thing, and people would care if you had an explanation for this, for these and other phenomena. But maybe we can talk for longer in private. So I don't want to hijack the conversation. Thank you.
Any other questions or comments? If not, I have a comment because of the last slide of your talk, Elena. I see on the slide the two categories of triangulated categories and the two categories of abelian categories. Now, there is a kind of universal way to pass from a triangulated category to an abelian category. And this is a link with the talk by Cipriano, because if you take the exact completion of a triangulated category, you get an abelian category, and the embedding of the triangulated category in its completion is the universal homological functor. So this is a kind of, I don't know if it is a two-functor or it is a two-something from triangle to ab-cut. And so it could be interesting, maybe not trivial, to study if these constructions this construction preserves some kind of two kernels, two cokernels, or the exactness property. I mean, when we study category theory, we have an object, in your case is a two category, another object is a two category of Venn categories, and what could be very interesting to study how to pass from one to the other, and that is exact completion gives a kind of universal to something from triangle to abcat. Don't know if you have something in mind into this direction.
I think for now we have thought more about considering the two functor associating to every abelian category its derived category of complexes, and this preserves two kernels and two cokernels. But this other functor you are mentioning, I think we haven't considered yet. But it's definitely interesting to look into it, yes.
Okay, because it goes in the other direction.
Yes, yes.
Okay, other comments or questions? If not, thank you again, Elena.